right. Get started? Yeah. Ready.
Well, good morning, everybody. Is this thing on? Is it? Yeah. Okay. Welcome to day 2 of TASI. We liked yesterday so much we decided we would do it again. So Vincenzo is going to continue to tell us about the standard model and beyond.
Thank you. All right. Welcome, everybody. Before I start, I wanted to mention that I started adding something on the Google folder, the shared folder. There's some material, a couple of files with slides, and then some of the original papers. So you may want to check it out if you want to. So today we continue our path towards the standard model, and we'll do first. Strong interactions. The microphone is on. Can you hear me all right? Better? No. Anyway, so why do we need the so-called strong nuclear force? I need an answer from you. What's inside nuclei? So what's inside the nucleus? Go back to the 30s. Yeah, sorry. Is there
I heard an answer.
Quark and gluon, but yeah, I don't know yet about quark and gluon. So I'm in the 30s. The neutron was discovered, and protons were there. So it's known that inside the nucleus there are a bunch of protons and a bunch of neutrons. What's wrong with having a bunch of, and then all the other known forces, electromagnetism, right? So protons don't want to stay together. There's a Coulomb repulsion. So there has to be a strong force, right? So that's the origin of the strong nuclear force, the terminology. You need to bind protons, neutrons in nucleus with a radius. So if A is the total number of the sum of proton and neutrons, it's known that this scales pretty much like this: 1.2 Fermi, A to the 1/3. It's like you pack neutrons and protons in the sphere. And again, so this is the Fermi scale, 10 to the minus 13 centimeter. So the modern theory of strong force goes. The first attempts go back to Yukawa in the 30s. And the idea was that, again, by analogy with electrodynamics, where the electromagnetism is mediated by the exchange of a photon, the idea was that there's a new meson called the pi meson, mediates strong force. And again, you can think of it as these are your nucleon. You exchange a pi meson. There could be a potential, right? So if you compute this diagram, there's the pion propagator. You Fourier transform, you expect a potential with a range, some coupling, alpha pi n in front, and then 1 over r e to the minus m pi r. So the range is the inverse of the pion mass. So the pion mass was expected to be around 100 MeV, inverse Fermi, right, to bind. This was a hypothesis. The pion was discovered in the late 40s. So but it was from pion nucleon scattering, it was pretty clear that, pretty immediately clear that strong, this alpha pi n was of the order of 10 to explain data, scattering data. So perturbation theory, so there your analogy with QED stops, because alpha in QED is about 1/137. So it's tiny and perturbation theory works. So you need, the perturbation theory is not applicable, and you need to resort to other methods. In the meantime, historically, so this is a very quick historical overview and incomplete and biased. Many other, through pion nucleon scattering experiments, a lot of resonances were discovered. So you could excite new states. So the whole zoo of particles were discovered. But the situation was that people did not know what's the underlying theory, and they started developing all sorts of methods. So it was very interesting theoretical epoch. I'm not going to cover any of that. But the two developments I would like to cover is how, superficially still, is how this idea of substructure of the hadrons, of this strongly interacting particle, emerged. And so the idea of substructure came out from staring at the spectra. So there was something in the spectra of where the masses of this hadron line up, and then from deep inelastic scattering experiments. So let's first cover the first part, the spectra. So the idea is that regularities in spectra point to some symmetries of, let me call it, quote unquote, L strong, the underlying Lagrangian of strong interaction, even though we didn't know it, they didn't know it. So what are the most obvious regularities in the spectra? So proton and neutron mass were roughly the same. The difference is about 1.2 MeV, and they are 938 MeV. That's where the lightest is. Also the pions, pi plus, pi minus, and pi 0, with their masses, so this is about 1 GeV. Pion mass is about 100, the neutral is 135 MeV, the charge is 139 MeV. So they're also pretty close, right? So it's here's 2 states, the same mass. 3 states, the same mass. This already is a hint. So what does this remind you? Maybe an SU2. They're in one-to-one correspondence with representation of SU2. Remember spin. So the spin 1/2, spin 1 is 3 states, and so on. So the idea was that this could be different states according to this internal symmetry group, which is now was called isotopic spin, or isospin. So the birth of what we call today internal symmetries. Okay, so it started with Heisenberg, and then was with the discovery of strange particles. So it's, again, I'm not going to, sorry, really wants to intervene.
Working on that.
I'm not going to follow.
Something went wrong.
Does anybody know how to silence
I'm
this?
here to help. Get to this.
Yeah, okay. Turn the volume. Yeah, that's easy. I don't know. Anyway, right. So many more particles. So this points to. So let's see. Let me write it down. So the degeneracies in these point to SU2. At some point, strange particles were discovered. So they were called strange because they were produced with reaction times typical of a strong interaction, so very fast reaction, but then they would not decay on a very strong. And that's a hint that they were stable under strong interactions. There was a new concept quantum number according to the strong interaction that was called strangeness. And so these were the kaons, lambda. So with strangeness, it became, well, clear that the underlying symmetry group was some sort of SU3 symmetry group. The particles, the spectra were organizing with, it was not a perfect symmetry. The symmetry was broken, but they were organizing into representation of SU3. So for example, octets. So there are, this whole analysis culminated in 1964 with the quark. So the idea of quark substructure. Put forward by Gell-Mann and Zweig. So the idea is that there were, so everything was seen in the spectra was consistent with constituents of the hadrons that were spin 1/2 particles called quarks, and with following assignments. So I'm going to write them. They were called three of them, up, down, and strange. And you could, so the isospin quantum number, up and down are the two states in the 1/2, in the doublet representation, with the z component is plus 1/2 and minus 1/2. The strange quark was a singlet under isospin. They all formed a triplet under SU3. And then the charges, the charge assignments were fractional. So the up quark is plus 2/3, and the down, so in units of the electron charge, sorry, minus, so opposite to the electron charge. So, sorry, that's it, over the absolute value of the electron charge, minus 1/3. So in this picture, for example, the pi plus was a U bar D states, the pi minus U D bar. The proton was a U U D. The neutron was a U D D neutral. So you can check the charges. But of course, there were issues. So these are pretty astonishing, fractionally charged particles. The experimentalists went out and looked for them. And so you can somehow look for the ratio of, if you have appropriate magnetic fields and so on, you can look for ratios of fractionally charged particle over pions, let's say charged pion. And this ratio was like 10 to the minus 10 or smaller. So there's no evidence of these fractionally charged particles. So the other problem was, so the issues were, so let me write it here, issues. No quarks. Seen. And the other was with the problem with the spin, with the statistics. So it turns out that in the simplest way to put together, so it is particularly easy to see in this delta 3/2 plus plus. There was a state consistent with the U assignment with spin up, so that they adapt the spin was 3/2. And since it's the lowest state with this quantum number was a S wave in coordinate space, so the wave function seemed fully symmetric, right? So it's symmetric in spin, symmetric in flavor, the three U's, and orbital it was symmetric. So, but these are fermions, right? Spin 1/2 quarks. So what's going on? So it was a problem, right? So this. So these were the main issues with the quark model. These were mitigated by introducing a new quantum number called color. This was introduced around 1965 by a number of people: Hahn, Nambu, Greenberg, and Gell-Mann. And so, for example, so assigned is the simplest version of this additional quantum number that allowed to reconcile this statistics was, okay, assign, again, another SU3, but now color. So each quark comes with three versions, or 1, 2, 3, or red, blue, green. And therefore, you can make a totally antisymmetric wave function. For example, this was resolving this thing by basically giving, you would write it epsilon I j k u I u j u k according to this new quantum number, and everything else goes through. So this is now obeys Fermi statistic. So, but there was still an issue. This new quantum number has to be mysteriously confined, right? So the hadrons, again, in this picture, we introduce the color. Hadrons are singlet under color. And this was still fine. You could still write all the mesons as so the Q bar Q as a color anticolor, so you form a singlet, and all the baryons singlet like this under the color. So this was the picture from evidence of substructure from the spectrum and all that it led to. So it was a long way, right, to get to this picture. The other line of evidence that appeared, again, historically a little later, towards the end of the 60s, was that from scattering experiments, so substructure from deep inelastic scattering experiments, basically electron-proton, scattering electron on proton nuclear targets, and looking for an electron with a large change in energy and a bunch of hadrons, right? So this was the deep inelastic scattering. And again, this is a beautiful story. I can't do justice to it. But the statement was that you could interpret the results in terms of scattering of the electron on essentially free, nearly free constituents. They were called partons. So to write it here, d sigma, all the differential distribution, are consistent with scattering of electron on nearly free partons. And the partons were consistent with quarks, so spin 1/2 and charge assignment of the quark. Again, what was the interaction mediating that? So it was a electromagnetic interaction, right? So this is your proton, this is the electron. And the idea was that everything was consistent with hitting, so incoherent sum of hitting your quarks, for example, inside the proton. And so, again, so that was exciting and really now points to, so this quark seems something real. It's not just a group theory exercise. There was one big puzzle though, right? So this quark are supposed to be part of strongly interacting system. Why would they behave as nearly free? Why could you sort of predict the main features of this process by doing perturbative calculation in QED? So why nearly free? right? So, and here's where, oops, where's this? Yeah. Here's where the breakthroughs, a couple of breakthroughs. I can spell. So it was theoretically discovered that our friends from yesterday, the non-abelian gauge theories, have this property of asymptotic freedom. And I'll say a few words about this later. For now, so non-abelian Young-Mills what this means is that the coupling constant at high scale, when you probe your system at high momentum transfer, high energy, coupling constant tends to 0, decreases, right? So, and we'll see this in some detail. And then, then a bunch of people put 2 plus 2 together and then promoted the color symmetry, this SU3, to a local gauge symmetry. So it's like, oh, we have this to sort of explain all these features of the spectrum and so on. Why don't we make it a gauge theory, a gauge local symmetry, and look for the full, promote the SU3 color to a gauge group. So what that means is that for each, remember, so Q could be up, down, or strange at this stage. Other quarks were discovered later. So the idea is that each Q, right, has now 3. It comes in 3 states, 1, 2, and 3. So Q, or you can any transform under this group G color as e to the I now epsilon A of x, TA acting on Q. So now what are the TA? In this is called the fundamental representation. There are 8 generators of SU3 group. These are in this and they are 3 by 3 matrices. So they are the Gell-Mann matrices. So TA in this particular form are the lambda Gell-Mann divided by 2. Yeah, so.
There's a question.
Yes, sure.
Just to be clear, this matrix is acting on internal degrees of freedom inside the column vector, right?
Yes.
Q1 has 3 components, right?
No, Q1 is one component, Q2 and Q3. So it's Q is really a matrix, this 3-dimensional vector. TA are 3 by 3 matrices, so act on the 3 dimensional.
Because you're at Q equals UDS. I thought it was
No, sorry. Okay, so Q, the notation is Q could be up, down, and strange. For each of them, you get this one.
Just to remind you, some of the text is getting a little small on the exponents and stuff.
Yeah, thank you. Sorry. Okay, so now we can. So now, based on what we said yesterday, so now we remember we said yesterday that give me your gauge group. I have to introduce to write down in dynamics that is invariant under local transformation. I have to introduce spin 1 bosons, one in correspondence to each of the generators of the group. These are now called what we call now gluons, all right? And now let's, following the rules we set out yesterday, let's write the QCD Lagrange. So, I guess it was Gell-Mann who invented the name quantum chromodynamics. Chromo is Greek for color. So LQCD is going to be, so now, perhaps, going to be sum over Q equal U, D, and S at this point, but you can add any quark you want. Q bar I this slash minus mq q. So the covariant derivative here is G strong TA. So those are the, actually let me be even more explicit, lambda A, the Gell-Mann matrix over 2, A mu A. Sorry, I keep changing my mind. I'm calling this gluon G mu A. Okay? That's what gives the interaction. This will give us these vertices. The gluon typically is indicated as this spring-like thing, and these are the quarks, the solid line. Then we need to write the kinetic term or and self-interaction, as we learned yesterday, for the gluon. So G mu nu A, G A mu nu. A again goes from 1 to 8. And as we saw yesterday, I'm not going to write the field strength. It's written yesterday in the notes from yesterday. So we learned that gluons have to be massless to preserve gauge invariance. That's almost it. That's the QCD Lagrangian. If we stick to this principle that we'll use, that we only require gauge invariance and Lorentz invariance, there's one more term that we can write down. And so let me write it down. It's quadratic in the, and I think conventionally is written this way. Theta, for a reason that will become clear tomorrow or Friday, you pull out the 32 pi squared, G squared, 32 pi squared. And then you write basically epsilon mu nu alpha beta. This is the Levi-Civita symbol over 2. And then you write G mu nu A, G alpha beta A. This is perfectly fine, it's non-zero. So this is the so-called QCD theta term. Yep.
Just to clarify, this may be clear to everyone in the room, but you're using the letter capital G for both the potential, and then it has one index, and the field strength, and
Yes.
then it has two indices. But
Yes.
they're two different things.
Yes, they're two different things. Sorry, yeah, thank you. So yeah, let me be explicit. G mu nu A is del mu G nu A minus del mu G mu A plus, I believe, G strong FABC G mu B G nu C, and FABC are defined, I should have said, they're a property of the group, not of this particular representation, but they're a property of the group. TA is the commutator algebra of the group. Okay. So, right, now let's, okay, it's a homework. So one thing I'd like you to work out, to think about and work out is that now we are supposed to believe that this is the theory of strong interaction. Everything's supposed to come out of this. Let's now look at, remember the thing I mentioned at the beginning, the symmetries. How do we see, for example, SU2 isospin coming out of this Lagrangian density, written in terms of quarks? Or SU3 flavor, how does it come out of this? So this, I'd like you to think about it. So remember, we talk about it, we see it in the spectra. The bound states, the energy eigenstates of this object are the proton, neutrons, a pion, and so on. And they respect this SU2 symmetry. How does it come out of here? How do we see it from here? The hint is, look at what transformation, what global, now this is not a gauge symmetry, it's a global symmetry, unitary symmetry. So look at what you can do with the quarks. What freedom do you have to transform the quarks, right? So, and also, other hint, look at what kind of larger symmetry you get if you go to MQ equals 0. what's the largest symmetry group that you can write down. So that's about, while we're talking about symmetries of this Lagrangian, let's say a few words about the last term. So the last term is actually, it's possible to write it as a total divergence. So the divergence of a four-current. And so you would say, oh, yeah, we can throw it away. However, because of topology of this, non-trivial topology of this gauge theory, non-abelian gauge theories, you can't really throw it away. And I'm not going to go into any details about that. But the issue is, so now the main point is you have to keep it. And then once you keep it, you can look at its symmetry properties. It's invariant under Lorentz, under gauge. But if you look at its property under parity and time reversal, this is odd under P and T. One easy way, well, you can go and apply all the rules. But the easy shortcut to see it is that this thing, you can write, it's proportional to basically the electric field minus the chromoelectric and chromomagnetic field. If this were electrodynamics, so the abelian thing, this would really be E squared minus B squared. Now the chromo version, the color version of that is, so this is nice, under parity and time reversal goes back into itself. This thing, if you work it out in component of the chromoelectric, yes, sorry, yep.
Isn't the 1/4 G mu nu G mu, isn't that the chromoelectric minus chromomagnetic?
Yes, the G mu nu, not the G dual, yeah.
Oh, okay.
Sorry, yeah, sorry, is the arrow visible? And so this thing is proportional to E dot B, chromo version of it. And so you can see that under parity, E goes into itself, B changes sign, so this is P odd. And at the time reversal, you see what happens. So you can work it out. So, all right, so now you know the theory of strong interactions. The reason, one more thing, sorry, I forgot to say. If we accept this T violation, this term, you would probably see, you expect to see, and if theta is order 1, like all the other couplings, you would expect to see large parity and time reversal violating effect in strong interactions. And we don't see them. So experimentally, from bounds, from strong interaction, like stuff like the neutron permanent electric dipole moment, we know that theta is less than 10 to minus 10. And it's a mystery. The fact that theta also is related to, you can start with the original theta, but you also, when you diagonalize, you start from most general quark mass matrix, you put it in a form where the masses are diagonal and real, you induce, again, we will touch upon this on Friday, you induce an extra contribution to theta. So in reality, this theta is a combination of the original theta and the argument of the determinant of the quark mass matrix. So the reason why this has to be so small is unknown and goes under the name of strong CP problem. So any one of you who's working on axions better be familiar with this. And this will be covered in other lectures. Let's now talk about asymptotic freedom, some of the consequences of that Lagrangian. So I'll write here. So this is important to understand whether we can use this theory like, you already know the answer. We can't really use it like QED, perturbatively in all regimes, but there are regimes where you can really do perturbation theory. So you're all familiar with renormalization, right? You know, in quantum field theory, you start going beyond 3 level. There are divergences. You have to reabsorb them. And there's a procedure, somewhat arbitrary on the way you define the coupling constant, Right? This is called the renormalization scheme and scale. So you can typically you define your coupling. Your coupling by fixed by to the value of some cross section or some amplitude at a given scale, right? So you introduce a scale. If you do renormalization that way, it's sort of so-called momentum subtraction scheme. You introduce a scale by saying, oh, I define my coupling constant at that value from that experiment at a given energy scale. Great. If you do other schemes like minimal subtraction with dimensional regularization, there's a scale that enters when you want to use dimensionless coupling in D equal 4. And so this is mu. So no matter how you do it, there is some scale. Even if you start with a massless theory, there is a scale that you introduce in your went through the renormalization procedure. And therefore, you can ask, but the physics should not, any physical observable should not depend on you. This is your choice, right? This is an arbitrary choice. So there are, so from that, you can derive so-called renormalization group equations that tell you how your couplings flow with the scale, move with the scale. And so for the coupling constant, GS, and I'm going to use this thing mu. A mu could be either the mu of dim reg with MS bar, minimal subtraction, or could be the mu from any momentum subtraction scheme. So we write it this way. It's a function of beta of G. And you can, for example, so beta of G, I'm going to use the following convention. You can do calculation G cube over 4 pi squared minus beta 1 G to the 5th over 4 pi to the 4th, and so on. So how you compute this, just to give you some intuition, some of the diagrams that are involved is the usual thing. So you have to look at the, there's a quark. So the coupling, one way to define the coupling is, right, the tree level would be something like this. There's one loop correction. The curly lines are gluons, but then you also have to look at the external lag effect. So for example, you have to look at the gluon self energy. Now this is the same thing that you would do in QED. In QCD, you have to do this thing. There's also stuff like this. The gluon talks to itself because it's different gluon, right? They carry color. Each of these lines carries the color. The vertices have this F, A, B, C. So there's also ghost type thing, but just this is just to give you some intuition. So beta 0, the important thing is that beta 0 now is 11 times the number of color, which is 3 in this case, minus 2 times the numbers of flavors. In this case that I wrote there are 3 quark flavors, up, down, and strange, divided by 3. So you see that up to a very large number of one flavor, this is a positive thing. Therefore, the beta function is negative. That means that as I increase the scale, the effective coupling constant, the running coupling constant decreases, all right? So that's the property of freedom. And this is by the way, the opposite of what happens in QED, in quantum electrodynamics. The coupling constant, in that case, beta has opposite sign, has positive sign, and it blows up at some very large energy. I want to write down the solution of the RG to convince you how now this scale, this will now start to make sense with some of the stuff that we talked about yesterday. So now define alpha strong, like in analogy with the alpha electromagnetic, as G strong over 4 pi. Then the solution, and I write it alpha strong, function of Q squared, or mu squared, whatever you want, is 4 pi over beta 0, 1 over log of Q squared over some arbitrary, well, some scale, lambda Q, which we call lambda QCD. And lambda Q, so now we've traded the free parameter, the coupling, for a scale. This happened through this renormalization. So now the question is not what is the value of alpha strong, what is this a number, but what's the value of lambda QCD, right? So, and the value of lambda QCD, again, depends a little bit on the scheme you're using, how many quarks you have there, but is on the order of a few hundred MeV, let's say 350 MeV. That's your, and that's the scale roughly where this alpha strong becomes 1. At Q square of the order of that, well, actually it blows up, but at Q square of order 1 GeV, that's where alpha strong becomes of order 1, on its way of blowing up at very low scale. So you see, so this thing starts to reconcile all this phenomenological input. So it's high momentum transfer. This is perturbative. So, for example, I remember, I forgot the exact number, but alpha strong at mu equal the z-pole mass, z mass, so 90 GeV is something like 0.118, if I remember correctly. It's pretty small. You can do perturbation theory. Alpha strong at 1 GeV is 1. You better not, I mean, it's useless to do perturbation theory. So alpha strong, so this explains the asymptotic behavior of quarks in DIS, large momentum transfer. Already at few GeV squared, this becomes perturbative. On the other hand, at low Q squared, this becomes non-perturbative and has a chance to explaining confinement. This is, again, how all this paths converge and beautifully sort of make sense within this theory. So one, and again, this would be a set of lectures or, by itself, but I'd like to give you a sense of how confinement might arise. So you could try using non-perturbative methods that, for example, will be described by Fiala Shanahan later this week, in the month. You can compute the quark, anti-quark potential, right? If everything is perturbative, you can imagine a Coulomb-like 1/r behavior, but there is a confining, so again, this is trivializing confinement. There's much more to this. There is a component in V of r that grows with the radius. And sigma, now you can imagine, you can know dimensionally, is to be a mass squared. And guess what it is? It's going to be some number times what? Times lambda QCD squared. Okay? And so on the scale, again, a few hundred MeV inverse, this thing becomes strongly attractive and can't pull them apart. And that's, roughly speaking, confinement. So far, NC equal 3, the fact that there are 3 colors was only guessed by theoretical arguments. You may ask, well, how do we have some experimental evidence that NC equal 3? Of course, by now, plenty. One example is, for example, you can compute something like, so you can compute this thing, a ratio of the E plus E minus cross-section into hadrons which is large momentum, large center of mass of energy. You can really think of QQ bar pairs over the QED one for producing muon anti-muon. And now, if you, again, the diagram is the same. Here you can have mu or quarks, QQ bar. What changes here is the charges, the quark. So this, if that's the whole story, it would count number of colors, because for each quark flavor there are. And then sum over quarks, the quark charges squared, because there's a cross section, and then there would be correction, and so on, right? You'll do the exercise of showing that this is some, if you are in mass between the z pole and above the b quark mass. So there are 5 quarks in this theory: up, down, strange, charm, and quark. These things turn out to be 11/9, of course, this summation, times, of course, NC. And this agrees with the data remarkably well. So NC is 3. There are other, but this, I think this is the simplest one, the most intuitive, one of the most intuitive way to check with experiment. All right, so this brings me to, so it was a tour de force to go through QCD in like less than 1 hour, but I wanted to give you a flavor of how remarkably our predecessors got to this theory. And the theory, one thing that I want to emphasize, theory is very rich, extremely rich, far from understood in all the implications of that Lagrangian over there, they're far from being understood, right? So, because as we heard from Jesse yesterday, you should be able to derive nuclear physics out of that. But even if you're less ambitious, even deriving certain properties of hadrons, it's still very challenging. So, in this, the perturbative aspects are also quite crucial for collider phenomenology. So if you're interested in collider phenomenology, better know something about this as well, right? So it's QCD is an integral part of the standard model. It's very important. You will hear a lot more about the non-perturbative aspect, in particular the computation, lattice QCD, from Fiala Shanahan, I think next week. And you probably won't hear too much about other non-perturbative aspects of QCD and how some of us try to use effective field theory techniques, the approximate symmetries, or global symmetries of that Lagrangian, to go from quarks to nuclei. And perhaps this interests many of you, how we probe new physics beyond the standard model using nuclei. You have to somehow deal with QCD whenever you write down, because we write down the new theory in terms of quarks and gluons. So that's the importance there. So I'll pause here for a few minutes, and then we'll move into the electroweak sector. So if you have questions, comments, while I... No? Okay. So I'll start. So we need both. So we're going to... Sorry, I have... So in the Google folder, you'll find Fermi's original paper on weak interactions, actually the translation in English, which I didn't know. I found it only yesterday. because the original is known, you can read it only in Italian and German. So let me, and you'd also find in the Google folder something, there's a talk by Weinberg. He wrote it up as a proceeding called the V minus A was the key. It's actually a cute little thing that goes through the historic developments, the weak interaction. Here, I just, now what's the goal, right? So want to understand, so from beta decay, basically, to this mysterious SU2 cross U1. There's a neat path from beta decays to this, and the goal is to, I'll try to explain this to you in the next 30 minutes. So it's, again, Fermi's paper. So I'm going to describe really this early phase of the electroweak theory. Basically from 1934 to 1958. So 1934 is Fermi's paper. Along the way, many people generalized Fermi's paper. Importantly, in 1956, Lee and Yang wrote the most general version of not requiring parity, that these discrete symmetries are allowed. And then in 1958, there were the seminal papers by Marshak and Sadarshan and Gelman and Feynman codifying the V minus A theory, right? So the interesting thing, and this is actually the reason I'm spending time here on this point, is that they really were doing what we nowadays call effective field theory, but they didn't call it that way. So it's going to be EFT ante litteram, which is Latin for before the word existed, essentially. So, and again, it's going to be a simplified picture, but if you read Fermi's paper, some of these things, I'm going to translate to modern language what Fermi had very clear in his mind. So basically, the situation is the following. You have electromagnetic plus strong interaction, even though the details were not known. So this thing these two interactions mediate fast, quote unquote, processes. You can think of this as nowadays, this is the standard model, stuff we know. It's obvious, you have binuclear and stuff. And then along the way comes this weak processes like beta decay. So the weak forces mediates slower processes like beta decay. So in diagrams, and unfortunately I'm really bad at managing space, you can think of this in your, there's the photon, and these are any particle you know. Then these are the nucleons, and you have your pion exchange or whatever favorite theory back then was interaction, and then you have this new force, it's something like beta decay. I'm going to use as a prototype the beta decay of a free neutron going to proton, electron, and something called neutrino, which was introduced by Pauli to save energy momentum conservation, because it was in a two-body decay. So what you observed in beta decay is just a recoiling charge part, the nucleus, recoiling nucleus, and the beta, the electron. If this were a two-body decay, there's no freedom. The electron come out in the center with fixed energy. but there was an energy spectrum, and therefore the only way to reconcile is that you introduce a new particle with zero charge, electric charge, that carries away, that balances the energy momentum. So this is the situation. Fermi reasoning was, but there's something really, again, discovered by, and I want to share with you, reading the original Fermi paper. Originally, the theory, before Fermi, there was this idea that the electron emitted in beta decay was a nuclear electron. There were atomic electrons, but also some electrons binding to nuclei. And there were twice as many protons to balance the charge as well. So there was one of the models for nuclei and beta decay. So Fermi said, no, forget about this weird theory of nuclear electrons. I'm going to follow the analogy to QED, like a spontaneous emission of photons in atomic transition. And a theory with creation and annihilation. They create and annihilate neutrinos to the modern theory of weak interaction. So the idea, again, we would, translating those, is write down the most general interaction involving the fields or creation and annihilation operators for neutron, proton, electron, and neutrino. Can it be the most general? Well, we want to preserving Lorentz and charge conservation, U1 electromagnetic. Fermi originally also imposed parity, and he did a vector-vector. Okay? And then he talks about the following. He says, okay, now I have these fields. You could put operators involving derivatives, momenta, right, for momenta. He said, no. Stick to non-derivative, non-gradient interaction. And this was because of the hierarchy of scales. Because lambda weak, so there's supposed to be some scale of where the weak interaction is generated. It's much bigger because of the fact that the weak processes are slow. You can deduce that lambda weak is much greater than lambda nuclear. This is few hundred MeV, which is in turn much greater than your kinematical value, Q external, which is on the order of M neutron minus M proton. So this is 1 MeV. This is about 100 MeV. And the unknown lambda weak, all Fermi knew is that it's bigger because the processes are slower. And so I'm going to neglect, well, he doesn't say exactly this, but he says he's going to neglect anything that goes like Q over lambda weak. That's how we would translate it today. And so your L effective has to contain, in terms of this form, Cij over lambda weak scale. We'll talk about this lambda weak squared in a moment. P bar, gamma I, this is a gamma structure, neutron. E bar, some other gamma structure, neutrino field. So let's look at this. So this is the right thing, destroys a neutron, creates a proton, creates an electron, creates an anti-neutrino or something. It doesn't matter at this stage, but it creates a neutrino. If you insist on the analogy that these are currents, you pair produce particle. If you produce an electron, you produce an anti-neutrino, but it doesn't matter at this stage. And then this gamma ij belong to this set of identity, gamma 5, gamma mu, gamma 5. So the pseudoscalar, so scalar, pseudoscalar, vector, axial vector, and tensor structures. Fermi originally just wrote the vector, or equivalent to the scale. You even went to the non-relativistic limit, so there was only, you couldn't even distinguish vector, vector versus scalar, scalar. Okay? So, in its full maturity, the Lagrangian, it's been written down by Li and Yang. And again, this Li and Yang paper is in the folder. Do I have time? Yeah, I have some time to write it down.
14 minutes.
Yeah. So Li, Yang, 56. Yeah. So the notation is the following. Write a vector current or any structure for the hadrons. And then on the lepton side, you do whatever you have to do in a Lorentz invariant form, but do not impose parity or stuff like that. And call now CV gamma mu minus CV prime gamma mu gamma phi. New. So it's vector, 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 axial. Then you do axial. So again, the only thing that you're conserving here is Lorentz and charge, electric charge. Then you have axial, and now he calls this CA gamma mu minus CA prime gamma mu gamma phi. New. Right? Now it's clear, right? So if I go to the scalar structure, now you can tell me what I write here. You write CS times what? Identity minus CS prime gamma phi. And the same, now at this point it gets boring, right? Like SMEFT, when you have to enumerate all these operators. But I'm doing this because exactly that's what we're doing today. We are desperate. So Fermi didn't, back then they didn't know what was the theory, so they write down the most general thing. We do the same when you write effective field theory. So, E bar Cp minus Cp prime gamma 5 new. And there is in the end a tensor. I don't know why they picked 1/2. I'm just trying to copy there. New n, E bar, sigma mu nu, Ct minus Ct prime gamma 5, new. There's only one tensor. Yes, there's no. Forget about it. So this is what it is. As a homework, and also it's in the supplemental material. The result is in there. It would be interesting for you to work out the properties under discrete symmetries. What are the, for example, what are the conditions on the effective coupling so that you get P, C, and T invariants of this Lagrangian? The supplemental material has the result, but not the intermediate step. You should convince yourself that. So for example, if I get let me look at the first one. Under parity, the first goes into itself. The second one goes into itself up to a sign, right? So I could still live with an overall minus sign. Suppose I could rephase things, But if I have both CV and CV prime, I'm doomed. Parity is violated. Okay, so that's so what do you do with this Lagrangian? Like we do today with SMEFT, you go out and compare two data and try to get either, hopefully, well, either bounds or non-zero values. And so back between the 40s and 50s, the tool of choice were beta decays of nuclei and all sorts of hadrons. I'm going to frame the discussion in terms of the decay distribution. So pheno, total decay rates and differential distribution. Very important. If you have a three-body decay, you have a lot of things that can teach you. So starting with this, so they worked out the most general form of the decay distribution based on this Lagrangian, and then they compared to data. There's a couple of things I want to highlight. So d gamma in a nucleus, for example, is proportional to some function of the electron energy, then 1 plus, before integrating, right? I have something called little a pe dot p nu over e nu plus something called big A, the polarization of the nucleus, so the spin of the nucleus or the decaying particle, dotted into the electron momentum over the energy of the electron, and then many more. These two are particularly interesting because based on a number of determination of big A and little a, you could learn that the theory essentially is V minus A. Only vector and axial are there, and C, V and CV prime, CV is equal to CV prime, and CA is equal to CA prime. So you probably seen this, but maybe it's never, since it's a classic thing. So in 1957, Wu et al. Observed that A is different from 0. And therefore, parity is violated. So let's look at the transformation properties of this object under parity. The electron momentum under parity, the space reflection, goes into itself or minus itself. It's a vector, so under parity goes into minus itself. J, the angular momentum, under parity goes into itself. It's a pseudo-vector. So the thing is odd. If you see one of these parity odd correlation, means the underlying theory is violating parity. So what they did, it was the decay of, let me write it here. I mean, some of these things are really cobalt 60 going to nickel 60 plus E minus plus nu E bar. This nucleus had J equal 5. This nucleus is J equal 4. So the
Cobalt, right?
Cobalt.
Not carbon.
Cobalt, sorry. Put them in a magnetic field, so the nucleus is polarized. And then you look for, let's say, along the z direction. And then you can measure the charged particle in the end, the electrons. And what was measured was that the electron, you construct basically this asymmetry. You count electron up minus electron down, gives you a measure of A. A came out to be not just different from 0. It's really close to -1. And so parity is violated, but there's also information about the helicity. Given the angular momenta here, there's information about the helicity of the electron. Because, okay, there's a little bit of background about nuclear physics, but these were allowed because of fast decays. It means the electron and neutrino carry out 0 to our orbital angular momentum. So if you buy that L of the final state is 0, it's just the spins that they have to compensate this change in Jz. Therefore, the spin of the outgoing particle have to be in the positive direction. And so if the electron is moving downwards, its spin is pointing backwards. If it were massless, right? It has to point exactly backwards. So it's the helicity, H is -1. Okay, so basically these electrons here coming out with momenta like this, but their spin like this. So HE equal PE hat dot SE hat -1. Of course, this is one simple way of seeing. This was confirmed by a bunch of other experiments. There's also, and unfortunately, I don't have time to go into any detail. There's some in the supplemental material. Measurement of A also pointed to the fact, in looking at the angular distribution, so how does this neutrino and electron come about, to come parallel to each other or going in opposite direction? It was basically implied that the underlying theory had really V or A and V prime or A prime. It couldn't be scalar and tensor. Okay? So the summary is, and I'm sorry I couldn't go into more detail, but this is so beautiful. The upshot is that Fino implied the following picture. Basically, CV was on the order of, so again, which we parameterize as 1 lambda weak by dimensionality. Lambda weak was on the order of 300 GeV. CA was similar size to CV. And very importantly, CV prime was equals to CV, CA prime, all within experimental uncertainty. CA prime equal to CA. And then C scalar, C the scalar tensor over, let's say, CV less than %. So this is what, by the way, what we hope to do with SMEFT. Maybe we see some signal, and you can see that it's not all the operators, but it points to some. So what does this point to? Of course, points to new physics at the 100 GeV scale, the Fermi scale. Great. Much bigger than the proton mass. So this is how you hope to learn about new physics by doing precision experiment at lower energy. It also points, very importantly, to chiral currents. This condition here, it's chiral currents, CV equals CV prime, 1 minus gamma phi, 1 minus gamma phi. And you get both V and A, and therefore parity is violated. So basically, it's pointing to a V minus A theory of current, weak interactions. And so basically, all of this points to L weak being, and I think in the modern notation, we call this 1 over lambda V squared with some G Fermi up to normalization factor, in the where this current And I'll tell you what the current is. Start with the leptonic current, it's easier. Here, as an aside, I would have written, if I stick to the Li and Yang and Fermi, I would have to write it as P bar, gamma mu, then there's something like 1 minus, something that is not 1, it's called GA, gamma 5 over 2, neutron. But the fact that GA is not 1, we now understand it from it's a matrix element of a quark operator, right? In the bound state, it's a QCD effect. The GA gets renormalized from 1 to 0. If I were to write this current in terms of quarks, and again, within the quark model, you would write it as 1 minus gamma 5 on quarks. So basically, U bar, gamma mu, 1 minus gamma 5 over 2 D. Okay? So we're almost there. We're almost seeing the emergence of SU2. And we're seeing the emergence of a chiral. So what we're seeing two things from this. If I interpret this as, do you have like 2 minutes? Or?
You're a minute over, 2 minutes over, so just try to finish up.
Yeah, finish up. But we'll pick this up again tomorrow.